Good morning, students. Myself, Vijay Shankar from EC Department, Chapel Engineering College. Today, we are going to discuss about the polarization of a uniform plane wave. There are different types of polarizations: linear polarization, elliptical polarization, and the circular polarization. These are the three types of polarization we have. One is linear polarization, elliptical polarization, and circular polarization. The polarization of a uniform plane waves. Polarization of a uniform plane wave. So the polarization of uniform plane wave is defined as a time-varying behavior of electric field intensity vector E bar at some fixed point in the space along the direction of propagation. The polarization of a uniform plane wave is defined as a time-varying behavior of the electric field intensity vector E bar at some fixed point in the space along the direction of propagation. The direction of propagation is always in the Z direction, and the E bar is in the X and the H bar is in the Y. So consider a uniform plane wave traveling in the positive Z direction. Then the field vectors E bar and H bar lie in X, Y plane. Means E is in the X and H is in the Y plane, which is perpendicular to the direction of propagation of the uniform plane wave. Means in the three variables X and Z and Y, the X value and X direction and the Z direction and the Y direction. Okay. The E is in the X plane and the H is in the Y plane, and which is perpendicular to the direction of the uniform plane wave. The uniform plane wave is traveling in the Z direction, the wave is traveling in the Z direction. Remaining two are is perpendicular. So the X is perpendicular to the Z and Z is perpendicular to the Y and the Y is perpendicular to the X. Both the three are mutually perpendicular. Okay. Which is perpendicular to the direction of propagation of the uniform plane wave. Being an electromagnetic wave, as wave travels in a space, both the fields undergo some variations with respect to the time. There are different types of polarizations of a uniform plane wave as given as linear polarization, elliptical polarization, and circular polarization. There are the three different types of polarization of a uniform plane wave. One is linear polarization, second one is elliptical polarization, and third one is a circular polarization. So in other words, the polarization is nothing but a way in which the magnitude and direction of electric field varies. Is nothing but a way in which the magnitude and the direction of electric field varies. These variations of field are observed in the direction of propagation of the wave. So if the variation of electric field is observed on a plane of perpendicular to the direction of propagation of the wave, we get E bar along the straight line or circle or ellipse. That is, it depends upon that. The line is nothing but a linear. Circle means is nothing but a circular polarization. If it is an ellipse, it is an elliptical polarization. It's a variation of the field are observed in the direction of the propagation of the wave. So if the variation of electric field E bar is observed on a plane perpendicular to the direction of the propagation of the wave, we get E bar along the straight line, nothing but the linear polarization. Circle, nothing but it is a circular polarization, or it is an ellipse, the elliptical polarization. The basic concept of the polarization of a uniform plane wave is, let us assume that E bar is resulting in the EX bar and EY bar, where EX bar and the EY bar are directed along the X direction and the Y direction respectively. Also assume that the variations of EX bar and EY bar be the sinusoidal similar to the E bar. To get different types of polarization for E bar, consider different conditions for EX bar and the EY. Okay, let us take the first one is a linear polarization. In this, the electric field has only the X component and Y component of E bar is a 0. So we are taking that is a EX bar and the EY bar. In this linear polarization, consider that E bar has only the X component and Y component of E bar is a 0. Then looking for that from the direction of propagation, the wave is said to be linearly polarized in the X direction. So from the direction of propagation of wave is said to be linearly polarized in X direction. If suppose similarly, if only the Y component in the E bar is present and X component of E bar is a 0, then the wave is said to be linearly polarized in Y direction. Okay, so which one is considered? X is considered means linearly polarized in the X direction. So Y is considered means X is a 0. So in that case, the linearly polarized in the Y direction. Depends upon the direction of the propagation of the wave is said to be the linearly polarized in the X direction means E bar has only the X component. And the direction of propagation of the wave is said to be in the linearly polarized in the Y direction means the electric field E bar has only the Y component. Okay. You see here the linearly polarized the E bar with an angular theta. So let us assume that both the components E bar are present by the EX bar and the EY bar. Both these components are in phase, having different amplitudes. In phase means nothing but the 0 phase. As EX bar and the EY bar are in phase, they will have their amplitudes reach maximum or minimum value simultaneously. Okay. Also, if the amplitude of EX bar increases or decreases, the amplitude of E bar also increases or the decreases. In other words, at any point along the positive Z direction, the ratio of amplitudes of both the components is constant, as both of them are in phase, have same wavelength. So we have the EX and the EY, and its amplitudes either increases or the decreases when it is along the positive Z directions. The ratio of the amplitudes of the both components are constant. The electric field E bar is a resultant of EX bar and EY bar, and the direction of it depends on the relative magnitude EX and EY. The angle made by the E bar with the X axis is given by theta is equal to tan inverse EY by the EX. The EX and EY are the magnitudes of EX bar and the EY bar respectively. This angle is constant with respect to the time. In other words, see, these are very important information. Now here, in other words, the resultant vector E bar is oriented in the direction which is constant with the time. Thus, the wave is said to be linearly polarized. And the wave is said to be the linearly polarized. The ratio, the tan inverse EY by the EX. The opposite side, tan theta is equal to EY by the EX. Okay. When both the components have the same amplitudes, we get the polarization of E bar as a linearly polarized the constant angle of 45 degrees. Got it, my students? 45 degrees angle. Thus, when EX bar and EY bar components are in phase with either equal or unequal amplitudes for a uniform plane wave traveling in Z direction, the polarization is linear. You have to write this definition. Or otherwise, the resultant vector E bar is oriented in the direction which is a constant with the time. Thus, the wave is said to be linearly polarized. When EX bar and the EY bar components are in phase with either equal or unequal amplitudes for a uniform wave, plane wave traveling in Z direction. The polarization is linear. Okay. Then for second one is elliptical polarization. Elliptical polarization. Consider that the electric field E bar has both the components which are not having the same amplitudes, and are not in phase. This is very important. In the linear polarization, its amplitudes are equal or unequal amplitudes, but they are in phase with either equal or unequal amplitudes. For a uniform wave traveling in Z direction, the polarization is called a linear polarization. Now here the elliptical polarization, consider the electric field E bar has both the components which are not having the same amplitudes and are not in phase. Okay. We are saying here the equal amplitude or unequal amplitudes, but here in the elliptical polarization, which are not having the same amplitudes and are not in phase. As the wave propagates, EX and EY bar will have maximum and the minimum amplitudes at different instants of time depending upon the relative amplitudes of EX and EY at any instant of time. In other words, the direction of resultant of E bar varies with the time. If the locus of the endpoints of the E bar is traced, it is observed that the E bar moves elliptically. The direction of the resultant field E bar varies with the time. If the locus of the endpoints of the E bar is traced, it is observed that the E bar moves elliptically. Then such a wave is said to be elliptically polarized. See the previous case, the angle of EX and the EY is 45 degrees. When the amplitudes of EX bar and the EY bar are different, and the phase difference between the two is other than 90 degrees, then the axis of the ellipse are inclined at an angle theta with the quadrants. And this phase difference between the EX and EY is exactly 90 degrees. Then the axis of the ellipses lie along the coordinate axis. Okay. Let us consider the amplitudes of EX and EY are unequal. Here it is not at all the equal. In a linear phase, either it is the amplitudes are equal or the unequal, but here exactly we can say that is the EX bar and EY bar components are unequal, and there is a phase is in phase. Let the phase difference between the two components be there 90 degrees exactly. There it is in phase, and here it is a 90 degrees in phase. 90 degrees phase, not in phase. Sorry, 90 degrees phase difference between the two components. The maximum amplitude of EX bar and the EY bar will occur at a different instance of the time. Thus, the direction of E bar varies with time along an ellipse. You see here, these figures we have when it traces moves towards the direction the EX and the EY bar. It looks like an ellipse here. You can trace the points 1, 1, 1 point in the clockwise direction or the anti-clockwise directions. It looks like it traces, it can get the elliptical. With the 90 degrees phase difference between the EX bar and the EY bar, the major axis of an ellipse lies along the y-axis if the amplitude of the EY bar is greater than that of the component of EX. If the major axis of an ellipse lies on the x-axis, if the amplitude of EX bar is greater than that of the EY bar. Okay, the major axis of an ellipse lies along the y-axis. Let us see here. This is a major axis, and this one is a minor axis. If the major axis, let us see here, if the major axis of an ellipse lies along the y-axis, if the amplitude of EY bar is greater than that of the EY bar is greater than that of the EX bar. If is a y direction. If the major axis of an ellipse lies along the x-axis, if the amplitude of EX bar is greater than the EY bar. The two cases here. Y-axis means EY bar is greater, and along the x-axis is a major axis of the ellipse. EX bar is greater than that of the EY. Thus, when the components EX bar and EY bar of unequal amplitudes have a constant, a non-zero phase difference between the two, it's not the zero. In phase means it's a zero, my dear students. It's a non-zero phase difference between two. For a uniform plane wave traveling in the z direction, the polarization is elliptical polarization. Okay, with a 90 degrees phase. Linear polarization have in phase and equal and unequal amplitudes. For a uniform plane wave traveling in the z direction, the polarization is linear polarization. And the elliptical polarization means when the components of EX and the EY of unequal amplitudes have a constant non-zero phase difference. Non-zero phase difference means it is not at all equal to the in phase. Let the difference is a 90 degrees here. For a uniform plane wave traveling in the z direction, the polarization is elliptical polarization. Okay. The third one, then the last, the circular polarization. Let us consider E bar has two components, EX and EY, of equal amplitude, but the phase difference between them is exactly the 90 degrees. Previously, it is unequal amplitude. So now here the equal amplitude. So linear polarization means either it is equal or the unequal. Elliptical polarization is unequal amplitude, and circular polarization of equal amplitudes with the phase difference is exactly the 90 degrees. At any instant of time, when the amplitude of any one of the component is maximum, then the amplitude of remaining component becomes zero. Means if X bar is component is maximum, EY is a zero. If EY bar is maximum, EX is a zero. Also, when any component gradually increases or decreases, the other component is gradually decreases or increases. Means one is increasing, means here it's a decreases. One is decreases means another one is a decreases respectively. Thus, at any time of the instant, at any instant of time, the magnitude of resultant E bar is constant, but the direction of resultant vector E bar changes with respect to the time, as the angle depends upon the relative amplitudes of the two components at every instance. If E bar is projected on a plane of perpendicular to the direction of the propagation, then the locus of all such points is a circle. Okay, when the center of the center on z-axis in one wavelength span, the resultant vector E bar completes one cycle of rotation, then such a wave is said to be circularly polarized. Such a wave is circularly polarized. You see here the diagrams we have. E bar here, and when it is moves towards a clockwise direction, and EY bar and the EX bar, then again it is in the x-axis. Then after it gets in the with another angle is a point EX and the EY here. The first of all, if I am taking that, it's a E bar is in the Y direction. Then it moves is a 45 degrees E bar and the EX bar. Then after it is in the EX bar. Then again 135 degrees EX bar and the EY bar. Then it's a 270 degrees. They trace all the points, circular polarization of EX and EY having the equal amplitudes with the exact 90 degrees phase difference between the two. It traces as a circular polarization. Okay, this is in the clockwise direction. When it is in the anti-clockwise direction, see, let us the mathematically we can see if E bar having the components in the both the X and the Y direction, we can write as E bar is equal to EX as a magnitude and sine omega t minus beta z AX bar, and EY sine omega t minus beta z plus delta into AY bar, so volts per meter. Where delta is a phase shift between the two components. Phase shift between the two components. That phase shift is exactly, we can take it as a 90 degrees. Consider that the field E bar is observed at Z is equal to 0. Okay, and Z is equal to 0. Then the E bar becomes EX sine omega t AX bar and EY sine omega t plus delta into AY bar. If delta is equal to 90 degrees, pi by 2. Let us here the pi by 2, you can keep it here. The difference between these two, the components is exactly the 90 degrees. Now, when omega t is equal to 0, what happens here? The sine 0 is the 0. So EX bar component is a 0. EX bar component is a 0. And sine 90, you'll get the EY bar is a max. EY is equal to EX bar, the magnitude of EX is a 0 and magnitude of EY is a EY. Means here is a 1 value and this one is a 0. So E bar is equal to EY, the first one. And omega t is equal to 90 degrees. 90 degrees means so EX, the magnitude of EX is equal to 1 or nothing but it is, will get the EX. So omega t is a 90 degrees, sine 90 is a 1 and it is a EX. And here the 90 plus 90. 90 plus 90 is a 180, 180 is sine 180, this is a 0. So EY bar magnitude is a 0. So one is a maximum means another is a decreases. If it is increasing, it is a decreases. If it is increases, then it is a decreases. And when omega t is equal to pi, is a pi by 2, sorry, 90 degrees, pi, and EX, the magnitude of EX is equal to 0. Then sine 180 degrees is a 0. And EY, sine 90 plus 180. You get the minus of that. So EY is equal to negative direction. It is a minus EY. And similarly, the omega t is equal to 3 pi by 2. 3 pi by 2. Then it becomes of magnitude of EX is in the minus EX bar or the EX and EY is equal to 0. Got it, minus. It depends upon that. And these two max amplitudes are equal, but the phase we can take it is a 90 degrees phase. And when we can take the omega t is equal to 0, pi by 2, pi and the 3 pi by 2, you can trace it as a circle. Let us see here. And omega t is equal to 0, if it is the EX is equal to 0, and we have only the EY. See the EY on. Got it, madam? And omega t is equal to pi by 2, these are 90 degrees. Then EX. Now you get that EX and EY is equal to 0. And omega t is equal to pi 180 degrees. EX is equal to 0 and EY, you can see shows the direction is a negative minus EY. It is a positive X, positive Y, and downwards is a negative minus EY. And when the omega t is equal to 3 pi by 2, 3 pi by 2, what is the EX bar is a magnitude of X bar is in the negative direction of the X, the positive X. So like that, it is getting into the clockwise direction. Or you can trace one point here, then after here, and it moves totally. You can trace it as a circle. Got it, my students? So omega t is equal to 0, pi by 2, pi, and 3 pi by 2. As in the figure, it is clear that the resultant vector E bar rotates in clockwise direction such that the locus of all such points represents a circle. Okay, this type of polarization is called left circular polarization. Left circular polarization. Okay. If suppose, now if I am taking the 90 degrees difference is the delta is equal to minus pi by 2. Delta is equal to minus pi by 2. So minus pi by 2 means sine of minus theta is a minus sine theta. So when omega t is equal to 0, you see, you can write this equation here. E bar is equal to Ex sine omega t x bar. E bar is equal to, the first one is Ex sine omega t ax bar plus Ey into sine omega t plus delta into Ay bar. Now I am considering that it is a minus. So E bar is equal to Ex sine omega t ax bar plus Ey into sine omega t minus pi by 2. Now I am considering the negative value, Ay bar. If omega t is equal to 0, E bar is equal to omega t 0 means sine 0 is a 0. So there is no any component of Ex. Ex bar is equal to 0. And Ey into sine omega t is a 0. 0 minus pi by 2. The sine minus pi by 2. We get the negative value. So minus Ey. Okay. And if omega is equal to omega t is equal to pi by 2. What is in the E bar? The first term is a sine pi by 2 is a 1. So we have the Ex. And pi by 2. Pi by 2 minus pi by 2 is a sine 0 is a 0. Okay. And third one, sine omega t is equal to pi. Omega t is equal to pi means the first term, the sine pi is at 0 degrees. And here the pi minus pi by 2. Pi minus pi by 2 is a 180 minus 90 degrees is a 90. Sine pi by 2 is a 1. We get the positive value. And omega t is equal to 3 pi by 2. 3 pi by 2, it is a minus. And Ey is equal to, Ex is equal to minus Ex bar. And Ey is equal to 0. Okay. What is the first one at omega t is equal to? Let us see here the minus dy bar. The first one is a minus dy bar. So it starts here in the minus. Then it rotates in this direction. At omega is equal to pi by 2. At omega is equal to pi by 2. You'll get the Ex. Ex is a positive. So it rotates in this direction. The positive Ex bar and the y is a 0 there. Then after at pi by in the omega t is equal to pi 180 degrees, and again it moves in the positive y, Ey, in this direction here. Let us see the starting itself is a minus Ey bar, then the Ex, then Ey, and the last term here that omega t is equal to 3 pi by 2 is a minus. Okay, and we can trace all these points. We'll get a circle. So from the figure, it is clear that the resultant vector E bar rotates in anti-clockwise direction. Previously, it is a clockwise direction when we can take the delta is equal to pi by 2. Now, in this case, we can take the delta is equal to minus pi by 2. It is clear that resultant vector E bar rotates in anti-clockwise direction such that the locus of all such points represents a circle. This type of polarization is called right circular polarization. Right circular polarization means we can right side is a circularly related. Okay, is anti-clockwise direction. Clockwise direction means we'll get to the left side tracing. Okay, left circular polarization. Now it is a right circular polarization. We can rotate in the right circular polarization. Got it, my students? Then any electric wave has two components: a forward traveling component and backward traveling component. Note that the definitions of right and left circular polarization are obtained for the forward traveling wave. For backward traveling wave, the definition of right and left circular polarization are exactly opposite to the previous. Thus, when two components EX bar and EY bar of equal amplitudes, remember my dear students, the definition here, when the two components EX bar and EY bar of equal amplitudes, if unequal amplitudes have a constant and non-zero phase difference of 90 degrees between them, for a uniform plane wave, the polarization is a circular polarization. But in the elliptical polarization, it is when the two components of EX bar and EY bar of unequal amplitudes have a constant of non-zero phase difference between them. For a uniform plane wave, the polarization is elliptical polarization. But in the linear polarization, when the two components of EX bar and EY bar are whether it's equal and unequal, and in phase, the phase difference is the in phase. For the uniform plane wave, the polarization is linear polarization. Remember this. These are the three definitions you have to write in whenever they ask in the part A, the simple definitions. Okay. And this for the circular polarization, the definition. And for elliptical polarization, so when the two components, see this one, when the two components of EX bar and EY bar of unequal amplitudes have a constant and non-zero difference between the two, non-zero phase difference between the two for a uniform plane wave traveling in Z direction, the proper polarization is elliptical polarization. Here unequal amplitudes, there it is a equal amplitudes, both are in the non-zero phase difference zone. And now the linear phase, when the E bar and EX bar and EY bar components are in phase with either equal or unequal amplitudes for a uniform plane wave traveling in Z direction, the polarization is linear polarization. Okay, these are the three definitions for the different types of polarization. One is a linear polarization, elliptical polarization, and circular polarization. Okay. Then so another topic you can go for, that is a surface impedance. Surface impedance. In many applications, the concept of surface impedance is required. At the surface of the conductor at high frequencies, the total current gets totally confined to a thin sheet. The surface impedance is defined as, you can see the definition of the surface impedance. Surface impedance is defined as the ratio of tangential component of electric field E tan to the surface current density. Surface current density is Js at the conductor surface. Okay. The surface impedance is defined as the ratio of tangential component of electric field E tan to the surface current density Js at the conductor surface. The surface impedance is denoted as Zs. Impedance is nothing but Z only. The surface impedance we call it as suffix Zs is equal to E tan by Js. According to the definition of surface impedance. E tan is a tangential component of electric field which is parallel to the surface of the conductor. The surface current density Js is a linear current which is a resultant of the tangential component E tan. This indicates that the total conduction current per meter width flowing in the thin sheet. Let us consider a flat plate conductor with its surface at Z is equal to 0 plane. Z is equal to 0 plane means like this. This is Z is equal to 0 plane. There is a flat thin conductor at Z is equal to 0. This is the direction. And here it is a Y and the X. Okay. Then the current distribution in the Z direction means towards like this. The current distribution in the Z direction through this surface, what we are assuming here is the surface is on the Z is equal to 0 plane. The current density J is equal to as a magnitude of J naught, and it is propagated, nothing but it is in the Z direction. So e power minus gamma is a propagation constant in the Z direction, where J naught is a current density at the surface and gamma is a propagation constant. J is equal to J naught into e power minus gamma into Z, where gamma is a propagation constant with the attenuation constant of alpha and the phase constant beta. Is a complex function. Gamma is equal to alpha plus I or J into beta. Now, it is exponentially decaying function. It looks like the graph between the Z and the current density J naught into e power minus gamma into Z. Okay. At Z is equal to 0, there is a surface here, the flat plate conductor, and surface of the conductor here, the Z direction, and here the X at Z is equal to 0. Note that the thickness of the conductor is assumed to be very large as compared to the depth of the penetration of the conductor, so that the reflection from the backside surface of the conductor is not possible, and the linear current density is given by the Js is equal to, we are taking from 0 to infinite only, because it starts at the Z is equal to 0, 0 to infinite. With respect to the Z, J naught into e power minus gamma into Z dz. Is surface current density Js is equal to the area under that J naught into e power minus gamma into Z dz. So with respect to the Z, we are applying the integral and the limitations also from the 0 to infinite. J naught is the constant, e power minus gamma into Z, and Z coefficient is a minus gamma. The upper limit is infinite and lower limit is 0. Js is equal to, we got J naught into, can substitute upper limit infinite, e power infinite is a 0, and the lower limit is a minus of minus is a plus, e power 0 is a 1, and we'll get the J naught by the gamma. Js is equal to J naught by gamma. But at the surface, the current density is given by, we know the J is equal to, the formula we have, sigma into E. Sigma into E. That will get in the JC bar plus JD bar, the one of the Maxwell's equation, my dear students. JC bar, it is a J into E bar, sigma into E bar plus JD bar, dou D bar by dou T. Dou by dou T means it is a J omega into epsilon into E bar, sigma into E bar. Okay, this will know a modified Ampere's circuit law. Del cross H bar is equal. Got it? So, but at the surface, the current density is given by the J naught is equal to sigma into E tan. Then the Js is equal to, what is the Js now? The J naught, you can take it as a sigma into E tan by gamma. Substitute the Js in the surface density definition. What is the surface density definition here? Zs is equal to the ratio between of tangential component by Js. What is the Js? We got E tan by Js is sigma E tan by gamma. Okay, substituting the Js in the equation 5. From the equation 5 in equation 1, we get that Js is equal to E tan and E tan get cancelled. Then Zs is equal to, here the sigma and the gamma is at gamma by the sigma. Okay, Zs is equal to gamma by the sigma, where gamma is a propagation constant and sigma is a conductivity. Zs is a surface impedance. Okay, my dear students. The surface impedance now it is a Zs is equal to gamma by the sigma, where gamma is a, we know the gamma, the propagation constant in terms of the variables j omega mu into sigma plus j omega epsilon, and the conductivity media is gamma is sigma is very much greater than the omega c, because here it is conductivity is more compared to the dielectric. The gamma is equal to under root of j omega mu sigma only. So we are eliminating the j omega epsilon. So Zs is equal to surface impedance. Gamma is j omega mu sigma by the sigma. And here the root sigma is there in the denominator sigma. We'll get the root sigma in the denominator. J omega mu by the sigma. It's totally under root. Zs is equal. Okay. And but the good conductor, the intrinsic impedance is given by the same. What is a good conductor? Eta is equal to the formula we have. J omega mu by sigma plus j omega epsilon. See, the conductivity is more compared to the dielectric, means we are eliminating the j omega. The eta is equal to j omega mu by sigma 1. Means now the intrinsic impedance and the surface impedance both are equal here. Zs is equal to intrinsic impedance 1. Got it, my dear students? As for the equations 8 and 9, the surface impedance and the intrinsic impedance, it is clear that for a good conductors, the surface impedance of a plane of conductor with a thickness greater than the skin depth of the conductor is equal to the characteristic impedance of the conductor. Zs is equal to the eta. Zs is equal to the eta function. Okay.